Hello everyone. Today we will be discussing the lab assignment 1 solutions of numerical analysis and design. So let's start. My name is Siddharth Gupta and my roll number is IT2K2482 and my enrollment number is DE2402061. So the first question was for finding the roots of the polynomial equation. The equation was x square. We need to write the algorithm for finding the roots of polynomial equations. So firstly, we need to write the algorithm for finding the root of equation using bisection method. So the assumptions we require that the function must be continuous on the interval a comma b, and fa and fb must have opposite signs. That is fa into fb less than zero. You already know that for the roots to be existed, the fa into fb, the function at 2 points must be negative for the roots to be exist at a to b. So these are the assumptions we are requiring. Next, the geometrical interpretation. The method brackets the root by repeatedly bisecting the interval. Geometrically, it cuts the x-axis segment in the half when the curve crosses the x-axis, narrowing down the bound until the exact crossing point is approximated. So it will cut the interval in half, then again in half, then again in half. So it will repeatedly bisect the interval until the required root is found. Now the algorithm for bisection method is: first we will read the bounds a, b, and tolerance e. E is normally 0.0001. A comma B are the 2 points between which the roots are lying. We will compute A, FA, and FB. If FA into FB is greater than equal to 0, we will print that it is the interval is invalid and we will stop. Otherwise, we will calculate the mid, that is equal to A plus B by 2. And if f of mid is greater than mod of f of mid, absolute value of f of mid is less than E. What is E here? E is the tolerance value, that is 0.0001. Or B minus A by 2 is less than E. Print mid as root and stop. If FA into f of mid is less than 0, set B is equal to mid, else set A is equal to mid. And otherwise we will go to step 4. Then again, till this condition is false, till the condition doesn't become false, we will continue this. As the condition becomes false, as your value gets less than e, we will find the mid will be the value of the root and we will end. So this is a simple algorithm for bisection method, where first we will read this, compute FAFB, check if F into FB is, if F into FB is less than 0, then only we will we will calculate the mid value. We will calculate the mid value. We will calculate the mod of F mid less than E. Till mod of F is less than E, we will calculate F of A into F of mid. If it is less than 0, we will set B is equal to mid, else we will set A is equal to mid, and we will again go to step 4 and we will do this complete process till F of mid is greater than E. Okay. So the time complexity for bisection method is O big O of log B minus A by E, where E is the tolerance limit, and the convergence of bisection is linear. As you know, it will cut the x-axis in two parts. The space complexity of bisection method is big O of 1, as only a few variables are stored in the memory. So the second part is Regula-Falsi method. For Regula-Falsi method, again we will assume the same thing, that f of x must be continuous in a to b and fa into fb must be negative. That means roots must lie between a comma b. The geometric interpretation. Now instead of taking the midpoint as we took in bisection, it draws a secant line. For Regula-Falsi, it draws a secant line connecting a comma fa and b comma fb. The point where the chords intersect the x-axis is taken as the next approximation. So here a secant is that will be passing through a comma fa and b comma fb, and the point where the chord intersects the x-axis is taken as the next approximation. Now the algorithm for Regula-Falsi method is: first we will read a, b, and tolerance e. If fa into fb is greater than 0, same thing as we did in bisection, we will stop. Else we will compute x, that will be a into fb minus b into fa upon fb minus fa. We already know FB, FA, AB. We will contribute the X. This is X is same as M we calculated in bisection method. Then again the same thing till f of x mod is less than E. We will print X as the root and stop. If FA into Fx is less than 0, we will set B is equal to X. Else we will set A is equal to X. So it is very simple. First we will check if FA into FB is less than 0 or not. If it is less than 0, then we will come to next step. As we know, then roots will lie between A to B. We will calculate the value of x, that is a fb minus bfn upon fb minus fa, till mod of fx is greater than e. We will till mod of fx is greater than e, we will compute this. What we will do, we will continuously check f into fx. As f into fx is negative, we will set b is equal to x. If f into fx is positive, we will set a is equal to x. Then again we will go to step 3. Again we will calculate this x is equal to a b minus bfn upon fbfn. Again we will check that if mod of fx is greater than e or less than e. And if, as at the last iteration, as mod of fx becomes greater than e, we will print x as the root and we will stop. So this is the algorithm for Regula-Falsi method. The complexity comes out to be O of log of 1 by e, and the convergence is linear and faster than bisection. The space complexity is always big O of 1. Now we will come to the secant method. For the secant method, same assumptions. Fx must be continuous, and we will take two guesses, that is x0 and x1, but they do not need the bracket. They do not need to bracket the root. The geometrical interpretation will be same. Like there will be a secant that will be passed through a comma fb and b comma fa. The x-intercept of this line will become the next guess. If it does not enforce bracketing, make it faster but risking divergence. So this is the geometrical interpretation. For secant method, the algorithm: read the initial guesses x0, x1, and tolerance e. E is again that 0001, point 0001. Then we will calculate compute x2. X2 will be x1 minus f of x1 into x1 minus x0 upon fx1 minus f of x0. This is the x2. Till x2 minus x1 is less than e, we will print x2 as a root and stop. Else we will set x0 is equal to x1 and x1 is equal to x2, and next we will go to step. So till this is coming greater than e, we will compute the next step. As this comes less than e, we will print x2 as a. So this is a normal algorithm for secant method. The complexity for secant method will come around same. That will be O of log of 1 by e, and the space complexity will be O of big O of 1. The convergence for this is superlinear. As we know, the order of convergence for secant method is 1.61. The convergence will be superlinear. Next week, come for Newton's Raphson method. For Newton-Raphson method, again we will assume that fx is continuous and fx must be differentiable, and f dash of x must not be equals to 0. And initial guess we will take x0, that must be relatively close to the absolute. Geometrical interpretation: we will approximate the curve with its tangent line at the current guess. Here for Newton-Raphson, the geometrical interpretation is a tangent. So the tangent line will pass to the current guess x0. The x-intercept of the tangent line becomes a next. Better approximation is x1. So these are the assumptions and geometrical interpretation required for Newton-Raphson method. The algorithm for Newton-Raphson method is, again we will read the initial guesses x0 and tolerance will be e. We will compute fx0 and derivative of f dash of x0. The third step, if f dash of x0 is exactly equals to 0, we will print that there is a mathematical error and we will stop. We will calculate x1, that is the formula for Newton-Raphson method, that x1 is equal to x0 minus f of x0 upon f dash of x0. We have already found that f(x0), f dash of x0, and x0 we already know. If x1 minus x0 mod is less than e, we will print x1 as root and stop. Else we will set x0 is equal to x1 and go to step. So it is also very simple. We will read the initial guesses, find fx0 and f dash of x0. We will calculate the Newton-Raphson formula, and till x1 minus x0 is greater than e, we will follow this, that we will set again and again x1 to x0, x1 to x0, x1 to x0, and again we will find this x1, again we will find x1, again we will find x1, and as x1 minus x0 becomes less than e, we will print that root is x1. So here we can find the root using algorithm for finding the root using Newton-Raphson method. The time complexity is O of log of 1 by e, and the convergence is quadratic. The space complexity is big O of 1. Now we come to next and last, that is fixed point iteration method. For fixed point iteration method, again we will assume that the equation fx0 can be rewritten as x is equal to gx. We can write the equation in the form of new equation, that is x is equal, like we can write x square minus x. minus 1 is equal to 0 as x is equal to x square minus 1. So we can write the equation as that. That is the assumption. The second assumption is the mod of g dash of x is less than 0, that near the root, to ensure convergence. Now the geometric interpretation, find the intersection of the curve this and this. The sequence form of cobweb or staircase pattern converging the intersection point. So the geometrical interpretation of this will be that there will be two curves and both curve will be intersecting, and the sequence will be a staircase pattern. So the next, moving on to the algorithm for fixed point iteration method. So the algorithm is again that rewrite fx is equal to 0 as gx is, like I told, we will rewrite the function in the x is equal to gx form. We will read the initial guess x0 and tolerance e. We will calculate that x1 is equal to g of x0. Again this thing again. Then again, if x1 minus x0 mod is less than e, we will print x1 as root and stop. Otherwise, we will set x0 is equal to x1 and go to step 3. So again, the thing is that only till x1 minus x0 is greater than e, we will do this and go again and again to this. And as x1 minus x0 becomes greater than e, we will print that x1 is the root and stop. Set x0 is x1 and go to step 3. So we will go to step 3 again and again. We will put x1 is equal to g of x0, x1 is equal to g of x0. Again and again, we will put x0 is equal to x1. Again, we will put x0 is equal to x1, and again we will calculate x1. So this is the fixed point iteration method algorithm. The time complexity, here will be the linear convergence, heavily dependent on the chosen g of x, and space complexity will be O big O of 1. Convergence of this will be linear, and it will be heavily dependent. It will depend on the function you took, like how you converted fx into gx. So this is the time complexity of fixes. Now we have already did the question number 1. That was the finding the algorithms for finding the roots of polynomial equation. Now moving on to question number 2, that is applying interpolation. The first part is writing the algorithm for Lagrange interpolation. For Lagrange interpolation, the assumptions we require are there are data points xi and yi. There are many data points given to us, and points do not need to be equally spaced. As we already know, for Lagrange interpolation, we do not need equidistant values. So these are the assumptions we require. The next is a geometrical interpretation. It constructs a polynomial of degree n that passes exactly through n plus 1 given data points by creating a linear combination of basis polynomial. So the geometrical interpretation of Lagrange interpolation is that it will construct a polynomial of degree n that will pass through exactly n plus 1 data points by it will create a linear combination of basis polynomial. So this is the geometrical interpretation. The next we moving on the algorithm for Lagrange interpolation. We will read n, that is number of points. We will read the arrays x and y, what are the values of x and y given in the table, that will be read as the array. And if the number of data points like 7, 8, 9, 10, what are the number of data points given? We will read xp, that is the point of interpolation, like we need to find f of 9, f of 10, that will be the xp. We will read xp. Now initially we will initialize the sum is equal to 0. We will start a loop for I is equal to 1 to n in steps of 1. We will set p is equal to 1, that is product we will set as 1. For j is equal to n, another nested loop inside this loop. For j is equal to 1 to n minus 1, we will say if I is not equals to j, p will be equals to p into interpolated value minus x of j upon xi minus xj. That is the formula for finding the Lagrange interpolation. And then we will sum up this sum plus this p value into y of I. Y of I you already know, like y of 1, y of 0, y of 2, y. So this is the algorithm for Lagrange interpolation. It is very simple. We will read the number of data points, we will read the arrays, we will read the point of interpolation, and inside sum is equal to 0. Find the for loop where we will put p is equal to 1. Start a j loop where we will this will be the value of p, and we will add the value of p into sum by multiplying into y. So it's a Lagrange interpolation algorithm. The complexity, as you already know, there is 2 for loops. So the time complexity will be big O of n square, and the space complexity will be big O of n. So it is a Lagrange interpolation. Next, moving on to Hermite interpolation. Next, moving on to divided difference table. Divided difference we already know. We will like Newton's divided difference interpolation. So we already know that assumptions that will be required, that data points are completely arbitrarily, that data points can be unequally spaced. Or you already know for divided difference and for Newton's for Lagrange's interpolation, you know there can be non-equidistant data points. The geometrical interpolation will be calculate the discrete analog of derivatives. The table provides coefficients of Newton's divided difference interpolation polynomial. Moving on to the algorithm of divided difference table, we will read n, again n number of data points as is x and y. That will be a table x values of x and y. We will create a 2D array that will be dd n of n. For I is equal to 0 to n minus 1, dd of I0 will be equal to y of I. And another loop for j is equal to 1 to n minus 1, and another nested loop for I is equal to 1 to n minus 1 minus j. dd of ij will be equal to dd of I plus j minus 1 minus dd of I j minus 1 upon x of I plus 1 minus x of I. And we will print the table dd and stuff. So this is the algorithm for making a divided difference table. So it is very simple. We will start a for loop from I is equal to 1 to n minus 1, and we will say that dd of the 2D array of I0 is equal to y of I. We will find another for loop of j is equal to 1 to n minus 1, and another for loop from nested for loop from I is equal to 1 0 to n minus 1 minus j. And this will be the formula for calculating the divided difference table, and we will print the table and stop. The time complexity, you could already see that it will be big O of n square, and the space complexity will also be big O of n square. So this is the Newton divided difference table. Next, moving on to Newton's interpolation formulas. So this is for Newton's forward interpolation. For Newton forward interpolation, we will assume that the data points must be equally spaced. As we already know, for Newton's forward backward interpolation, the data points must be equidistant. Or next, we are assuming that a difference table we have already been constructed. Now, the geometrical interpolation. The geometrical interpolation for Newton's interpolation formulas will be a polynomial by adding terms based on finite differences. Forward uses top edge differences, backward uses bottom edge. We already know forward uses we interpolate, we construct the difference table by subtracting the elements on the top. Here for backward interpolation, we construct the table by starting from backwards. So this is the geometrical interpretation. Starting with the algorithm of Newton forward or backward interpolation, we will ensure that there is a uniform step size h. We will create the forward difference table as I already told in our last video also. Then we will calculate u, that is xp, the interpolated value, minus the first value upon h is the step size. We will initialize the sum with 0, 0, and we will take a u term is equal to 1. We will find a for loop, start a for loop from I is equal to 1 to n minus 1, and we'll say that u of term will be equal to u of term into u minus I minus 1 by I. This we have already done. And sum is equal to sum plus u term minus into y of 0 I. And we'll print the sum and sum. You already know what is this u term is equal to u term into u minus I. This is like that as we have seen in formula for Newton forward interpolation, you can already say that it comes like u minus 1, u minus 2, u minus 3, u minus 4 divided by 1 factorial, 2 factorial, 3 factorial. So this is the way, this is the algorithm to find that. This is the algorithm for finding this. We will and why this we are multiplying the u term. Like first we have find it u minus 1, then again we need to find u minus 2, and we will multiply u minus 1 into u minus 2. So this is for that. And we will add these u terms into the sum by multiplying it from y of 0, comma, and we will print the sum. So this is the Newton's forward interpolation. The time complexity will be big O of n square for building the table, and for evaluating it will be big O of n, as you already see. The space complexity will be big O of n square for the table, and it will be reducible to big O of n for 1D array. Now the next was for Newton numerical quadrature formula. So we have already done 3 questions. Now moving on to the fourth question. The fourth question is for finding the algorithm for Newton numerical quadratures. Moving on with Newton codes formula, trapezoidal rule. The assumptions required are the function can be approximated by polynomials of degree 1, trapezoidal, or degree 2 Simpsons over small subintervals. Points must be equally spaced. So these are the assumptions required for Newton codes formula. Geometrical interpretation will be divides the area curve into simple multiple trapezoids. The total integral is the sum of area of these trapezoids. The geometrical interpretation, like if we have any curve, it will divide the curve into multiple trapezoids, and the area will be the sum of that trapezoids. So these are the now writing the algorithm for trapezoidal rule. It is very simple. We will read A, B, the limits A to B from where we have to integrate, and number of intervals, that is n. We will calculate h, that will be equal to b minus a by n. b minus a by n. will be the h. As you all know, what is b? B is the upper limit, a is the lower limit, divided by n is the number of intervals. We have calculated the h in this way. We will initialize the sum to fa plus fb. As you know, that initially in all the rules, whether it's a trapezoidal, Simpson, Riddles, the first part is y0 plus y. So it is that only. Fa plus Fb. First term plus last term will already be in the sum always. Next, we will start a loop x from I is equal to 1 to n minus 1, and we will say x is equal to a plus I into h, and sum will be sum plus 2 into fx. So we will start a for loop. X will be equal to a plus I into h, and sum will be sum plus 2 into f of x. Then the integral will be h by 2 into sum, and we will print the integral and stop. So this is the norm of simple algorithm for finding the integral of for finding the integral using trapezoidal rule. So here we have done this. Next, moving on to time complexity. Time complexity will be big O of n, where n is the number of intervals, and space complexity will be big O of 1. Next, moving on to Gaussian quadrature formula. For Gaussian quadrature formula, we already know that it integrates till -1 to 1. We will assume that the integral interval is normalized to -1 to 1, and fx must be smooth. The geometrical interpretation will be, instead of using fixed evenly spacement, it carefully selects the optimal nodes, roots of legendary polynomials, and ways to achieve exact integral of polynomials of highest possible degrees 2n minus 1. Now moving on to the algorithm for Gaussian quadrature. Okay, so first of all, we will transform the limits a comma b to -1 to 1. So for that, we will put the value of x is equal to 0.5 into b minus a into t plus b plus a into t. So and dx will be equal to 0.5 into b minus a into dt. So for first in the first step, we will transform the limits from this to this, and from transforming the limits from a comma b to 1, we will put x is equal to this, and we will substitute the value of x into the given function. Now, next, we will pre-compute weights and nodes for chosen n. It will already be given, or you can calculate the weights and the nodes for the chosen value of n. We will initialize the sum is equal to 0. We will start the loop from I is equal to 0 to n minus 1, and the sum will be equals to sum plus w of I into f of x of t of I. So from this, we will calculate the sum. The integral will be 0.5 into b minus a. The 0.5 is coming from this. B minus a is also coming from this into the sum we have formed. So from this, we will calculate the integral, and we will print the integral. So this is the general algorithm for Gaussian quadrature formula. The time complexity, as you can see, there is only one for loop from one I is equal to 0 to n. So time complexity will be big O of n, and space complexity will be also be big O of n. Next, coming to question number 5. Question number 5 is writing the algorithm for linear equations, Gauss elimination, Gauss Jordan, Jacobi, and Gauss seidel. So algorithm for Gauss elimination includes, first the assumption will be system is Ax is equal to B, and matrix is non-singular, that is determinant of A is not equal to 0, matrix must be non-singular, and leading principal minors are non-zero, that we are assuming here is no pivoting. Now the geometrical interpretation will be a system of intersecting hyperplanes into an equivalent upper triangular system allow easy extraction of intersection point via back substitution. So here the algorithm for Gaussian elimination is, we will first form an augmented matrix, then we will start a for loop from k is equal to 0 to n minus 1, and then again a for loop from k plus 1 to n minus 1, and the factor will be a of ik upon a of kk. Then for again a third loop for j is equal to k to n, a of ij will be equal to a of ij minus factor into a of kj. So from here we will this is the step of forward elimination. So this will convert your matrix into a upper triangular matrix. So for converting the matrix into upper triangular matrix, we will use these three loops, and we will do this. After this, the third step from I is equal to n minus 1 down to 0. Now we will back substitute. Whatever the values are there, we will equate it with the values on the right hand side, and we will find the values of x, y, and z. So for I is equal to 1 to n minus 1, sum will be equal to b of I, j is equal to I plus 1 to n minus 1, sum is equal to sum for we're starting a loop from I plus 1 is equal to n minus 1, and the sum is equal to sum minus a of ij into xj. Sum is equal to sum a of ij into xj and xi. Now we will print the values that will be equal to sum upon a of I comma I. So like this we have finded the algorithm. That is, first we will do back forward elimination, then we will do back substitution. So this is a simple algorithm for Gaussian elimination method. Time complexity, you can already see for elimination it is big O of n cube, and here it is big O of n, big O of n square. Yes, one is this and another is this. So big O of n square for back substitution. Space complexity is big O of n square. Next is Gauss-Seidel method. Sorry. For Gauss-Seidel method, we will assume that the matrix should be diagonally dominant or symmetric positive definite to guarantee convergence, and there is no singular system. So let's start with the algorithm for Gauss-Seidel. For Gauss-Seidel, we will read a matrix, a vector, a tolerance, and max iterations. We will initialize x of I is equal to 0. We will initialize x of I is equal to 0 for all I. For iteration is equal to 1 to max. We will initialize max of error is equal to 0, and for I is another for loop I is equal to 0 to n minus 1, we will say sum is equal to b of I. Then another we will start a for loop from j is equal to 0 to n minus 1, and if I is not equal to j, we will subtract the sum by a of I j into xj, and the new x will be sum upon a of I comma I. So like this, then we will start a for loop and we will print the value of x of I. So like this, it is the algorithm for finding the roots using Gauss-Seidel iterative method. Next, the time complexity will be k into n of n square, where k is the number of iterations, and the space complexity will be big O of n square. Now, moving on to the last question, that is writing the algorithm for ordinary differential equations. For ordinary differential equations, the first is Euler method. For Euler method, we will assume that the differential equation is in the form of dy by dx is equal to f of x comma y. The initial condition is y of x0 is equal to y of 0, and the step size is small enough to assume the slope is constant over the interval. Now, the geometrical interpretation will be, it will approximate the solution curve by a sequence of small segment lines where the slope of each segment is given by derivative evaluated at the beginning of the interval. The Euler method algorithm is very simple. We will read the values of x0, y0, target xn, and step size h. We will till we will start a while loop till x0 is less than x of n, like the starting value is less than ending value. The y of new will be equal to y0 plus h into f of x0 comma y0, and x0 will be equal to x. We will increase the step size by h, and y0 will be y0. We will print the y0 as the value at xn, and we'll solve. So it is very simple to find the root using to find the value using ordinary differential equation. So the only part is that the while loop will move from x is equal to 0 to from x0 to xn, like from starting to the ending. And this is the formula for Euler, that is y of new is equal to y of 0 plus h into f of x0 comma y0. Then again x will change by increasing the step size, and y will become new, and we'll print the value of y. So the time complexity for Euler method will be big O of n, and the space complexity will be big O of 1. Next, moving on to second part of the question, that is for writing the algorithm for Runge-Kutta fourth order. For Runge-Kutta fourth order, we will assume that the equation is ordinary differential and dy by dx is equal to f of x comma y. The second, that the graph is smooth, and the third, we will assume that it provides much higher accuracy than Euler by evaluating slopes at midpoint. Next, the geometrical interpretation. Instead of relying on just the initial slope, the Runge-Kutta fourth order takes a weighted average of slopes at the beginning, midpoint, and the end of interval to trace much more accurate path. So, Runge-Kutta is more accurate than Euler method. Next, moving on to the algorithm. Algorithm is very simple and it is as similar as Euler method. We will read x0, y0, target, exit, and step size, similarly as we did in Euler method. Till again, while loop we will form till x0 till x less than xn, as we did in Euler method. Then k1, that is the formula. These are the formulas for Runge-Kutta. K1 is equal to h into f of x0 comma y0. K2 is equal to h into f of x0 plus h by 2 comma y0 plus k1 by 2. K3 is equal to h into f of x0 plus h by 2 plus y0 plus k2 by 2. This k2 comes here in k3. K4, h is equal to h into f of x0 plus h comma y0 plus k3. This k3 comes here. Now y0 will be equals to y0 plus k1 and plus 2k2 plus 2k3 plus k4 by 6, and x0 will again become x0 plus h, and we will print y0 and so on. So it is very simple. Just read this, apply the while loop here, and print the value of y. So this is the algorithm for Range Kutta fourth order. The time complexity will be big O of n, and the space complexity will be big O of 1. So here have we have come to the end of the lab assignment 1 solutions, where we have seen the algorithm for each and every uh, topic or each and every method we have learned in this entire course, that is numerical analysis and design. So uh, thank you.